I'm Adam from RFOXiA from our real lab. Today we're answering, what does unified real-time output across 7 simultaneous sensor streams actually reveal that working with one sensor at a time cannot? Enjoy our new soundtrack at the end of the video. I want to start with a framing problem. When most developers integrate sensors into a system, they do it sequentially. One sensor working, verified, then the next one added, then the next. The mental model that builds up from this process is a list of independent readings. Temperature is a number. Accelerometer is 3 numbers. Air quality is a number. They exist in parallel, but they are conceptually separate. You pull them in sequence, you log them in separate columns, you analyze them in separate windows, and the system appears to work. The readings are there. The data looks reasonable. Nothing is obviously wrong. The problem is not that this approach produces bad data. The problem is that it produces incomplete understanding, and you do not know what you are missing because you have never seen it any other way. When you run all 7 sensors simultaneously and you treat their output as a single unified stream rather than 7 independent channels, the data says things it could not say before. I will give you a concrete example. An air quality spike. In isolation, an air quality spike on a ZMOD 4510 reading means something in the environment changed. You log it, maybe you flag it. If you are doing environmental monitoring, you probably just note the timestamp and move on. Now add the BMI 270 accelerometer to that same timestamp. If there is a high vibration event coinciding with the air quality spike, you now have a different interpretation entirely. The spike may not be environmental, it may be mechanical, vibration from a motor, a pump, a vehicle passing. These can cause sensor artifacts or stir localized particulate matter in ways that look like genuine air quality events but are not. You cannot distinguish between those two explanations with a single sensor. You can with 7 running simultaneously. This is not an edge case. This is the default condition for any sensor deployed on a moving platform. Drones, vehicles, robots, wearables, all of them generate mechanical context that makes environmental readings ambiguous without motion data sitting next to them in the same timestamp. The LPS2288 pressure sensor is another example of this dynamic. Pressure data on its own is useful for altitude estimation and weather monitoring, but pressure also responds to airflow. If you are on a drone and you are making altitude changes, the pressure reading and the accelerometer z-axis data should be correlated in a predictable way. If they are not, if the pressure is changing faster or slower than the altitude motion implies, that discrepancy is real information. It could indicate a sensor fault, it could indicate an unexpected aerodynamic condition, it could indicate a calibration drift. Without both streams running simultaneously, you cannot see the discrepancy. You only have one of the 2 numbers needed to compute it. The magnetometer from Texas Instruments adds a third layer to this. The TMAG 5273 is sensitive enough that electromagnetic interference from nearby motor drivers or power switching circuits will show up in its readings. Magnetometer anomalies correlate with specific phases of motor operation. Again, in isolation, that looks like magnetic noise. Alongside current draw data or PWM timing data, it becomes motor health monitoring. The sensors do not need to be designed for that application. They just need to be running at the same time. This is the core argument I'm making. The value of a multi-sensor platform is not additive. It is not that 7 sensors give you 7 times more data than one sensor. It is that 7 simultaneous streams create cross-correlation opportunities that do not exist when you query sensors independently. The relationships between channels are information. The timing of correlated events across channels is information. The absence of expected correlation is information. You lose all of that if your architecture treats sensors as a list rather than a unified stream. Now let me talk about the I2C architecture, because this is where most multi-sensor designs fall apart at the implementation level. The obvious failure mode when you put multiple I2C devices on a shared bus is address collision. 2 devices claiming the same address will conflict. The bus will return garbage or nothing at all. The way most developers handle this is by putting sensors on separate buses, or by using I2C multiplexers, or by buying modules that only have a few sensors on them so the address space stays manageable. All of these approaches work. All of them also add complexity, add wiring, add board area, and add latency if you are multiplexing. The Multinav Pro Plus Sensors module solves this at the chip selection level. Every sensor on this board was chosen with a dedicated non-conflicting I2C address. There is no multiplexer, there is no address remapping, there is one I2C line, and all 7 devices speak on it without interference. This sounds simple, it required careful component selection. The BMI 270 from Bosch SensorTech is at a specific address. The TMAG 5273 from Texas Instruments is at a different specific address. The LPS 22HH from ST Microelectronics. The MVH 4003D from MEMS Vision for humidity and temperature. The ZMOD 4510 from Renesas for air quality. None of them collide. You connect 4 wires, power, ground, SDA, SCL, and all 7 sensors are immediately addressable. The firmware overhead is minimal. The wiring complexity is minimal. The board footprint is 24 by 18 millimeters. I want to be direct about why this matters for the kind of developers watching this video. If you are building a drone, a robot, or any kind of field deployed monitoring device, board space and wiring complexity are hard constraints. Adding a 7 sensor array that requires separate buses, separate connectors, or a multiplexer IC is often the thing that makes a project not fit. The compact integrated design of this module is not a convenience feature. For a significant portion of the use cases it serves, it is what makes the use case possible at all. The data network integration adds a dimension that goes beyond hardware capability. When this module is deployed, that is what 7 simultaneous streams reveal when you treat them as a unified data source rather than a list. Now let me show you the actual hardware. This is the complete sensor array in a single module: accelerometer, gyroscope, magnetometer, temperature, air pressure, humidity, and air quality, all 7 running simultaneously on one board. This is not a sensor list, it is a unified environmental and motion intelligence platform in a 24 by 18 millimeter footprint. Motion and environment are not separate problems on a real platform. The BMI 270 handles motion at a resolution that matters for professional drone applications. The environmental sensors, temperature, humidity, pressure, air quality, run alongside it so you can see exactly what the mechanical context was at every environmental event. Every sensor on this board was chosen specifically. Bosch SensorTech BMI 270 for motion, Texas Instruments TMAG 5273 for magnetic field, ST Microelectronics LPS 22HH for pressure, MEMS Vision MVH 4003D for humidity and temperature, Renesas ZMOD 4510 for air quality. These are not commodity choices, each brings professional grade accuracy to its domain. 7 sensors, 1 I2C line. Each device has a dedicated non-conflicting address. No multiplexer required, no separate bus routing, 4 wires, power, ground, SDA, SCL, and every sensor is immediately accessible. This is the architecture decision that keeps the footprint small and the wiring sane. 24 by 18 millimeters, that is the entire board. For drone builds, wearables, and compact IoT deployments, where board space is a hard constraint, that dimension is often what determines whether a full sensor stack is even viable. This module makes it viable. Real-time output means every reading reflects current conditions, not a buffered average from 30 seconds ago. When you are reacting to environmental change in a moving system, timestamp precision matters. The unified stream from this module gives you the data and the moment it was true, simultaneously across all 7 channels. Robotics, environmental monitoring, drone navigation, precision agriculture, disaster response sensing, industrial IoT, data network contribution. The same 24 by 18 millimeter board applies across all of them because the underlying requirement is always the same. Know what your environment is doing and what your platform is doing at the same time. 7 sensor stream contributes verified environmental data to the RFOXiA data network, temperature, humidity, pressure, and air quality readings that pass verification against reference sources earn daily rewards. The hyperlocal second-level temporal resolution of that data is what enterprise buyers, agricultural technology companies, smart city operators, insurance risk modelers cannot get from standard weather APIs. Your deployed sensor node is doing science, and it is doing it at a resolution no existing infrastructure matches.
Seven signals in the dark. Every axis, every arc, the pressure dropping overhead, the temperature that overhead. The temperature that fills with dread. I feel the tilt before you fall. I read the field behind the wall. The story that the data holds, the story that the data tells. I sense what you cannot see. Magnetic heat, motion locked humidity, motion locked in real-time streams. The world decode not what it's. 7 sensors, one board, one truth. Every shift and every move, the invisible made visible now. The environment speaks, I know how. Ow. Gyroscope on the edge of flight. Accelerometer reads the night equality through industrial air. 3-axis matter, matter to where. Humidity shifts before the storm. Pressure maps the rising norm. All 7 running, all in sync, faster than you stop to think. I sense what you cannot see. Magnetic heat, motion locked humidity, motion locked in real-time streams.